So we've done integers, right? Positive and negative. We've done addition. We can do subtraction. Let's look at some of the other operations. So for example, how do we do multiplication? Okay. So this is the algorithm that we do in elementary school. And when we multiply numbers, what we do is we do it one digit at a time, right? So 7 times 24, that's 168. That's 24 times 7, right? And then this is 1 times 20, or 24 times 1 to be consistent, right? But shift it to the right by 1. Shifting to the right by 1 in decimal is the same as multiplying by 10. So this is actually 24 times 10, right? So really what we're doing is 24 times 17 is 24 times 10 plus 24 times 1, and the result is 408. Okay, so we do the exact same thing in binary, right? And this is how computers can multiply. Right? So 111 times 101, what we'll do is we'll take 111 and we'll multiply by 1. Ooh, that's easy. That's just copying it over. So we get 111, okay? And then this is 111 times 1. And this is 111 times 0, okay? And then shift by 1. And this is 111 times 1, shift by 2. And then we add those three numbers and we get the answer, okay? Adding those numbers, well, that's just a ripple carry adder, okay? And so we actually need about n minus 1 ripple carry adders, right? Here they are, right? You know, the first one, second one, and third one to be able to do it. So I'm adding three things. I need two adders to be able to add that. You need two n bits to the result, and that's just simply because when I multiply two n-bit numbers, the answer is a single 2n bit number, okay, or potentially that's as large as it needs to be. Shifting is pretty easy to do, okay. We can just connect wires diagonally, if you will, or you can actually build a shift circuit that will do it, okay. But notice that the multiplication is actually somewhat easier than decimal, because all we ever do is multiply by 1 or multiply by 0. So that's just copy or 0, right? And then shifting is easy. So I'm actually going to ask you to implement this algorithm in your programming assignment, okay? And all you'll have to do is implement a shifter, which is pretty easy. And you already have a binary adder, you know, a ripple carry adder, because, you know, we did that in class, so I'll just give you that code. And then you need the code that actually kind of combines these to be able to do multiplication. So I think you'll find that that's fairly straightforward. How about division? Okay, you learned an algorithm for division. That algorithm is called long division, and you may still have a nightmare or two about it. It's not easy, and it's one of the hardest things in arithmetic in elementary school. We could actually do that in binary. Another algorithm that you can do for division is just repeated subtraction. So what's 13 divided by 3? Well, 13, so divided by repeated subtraction by 3. So from 13 we go to 10, that's 1, 7, that's 2, 4, that's 3, 1, that's 4. So the answer is 4. 13 divided by 3 is 4. And by the way, I was left with 1, so that's the remainder. So we could do that, right? And I'm just going to suggest to you that that's what we do. That's what computers do. That's how they divide. Because we already have all the information for that. We already know how to subtract. Of course, you know that that's not the way that computers really do it. There are, in fact, faster and much more complex algorithms, but I'm just not going to cover them here. I mean, that's much more advanced material. Okay. Now, I want to say that, in fact, that's true of all the other operations. So the ripple carry adder, I guarantee you that's not the way that your computer actually adds numbers. Okay. We can do a lot better. So, for example, there's something called a carry save adder that's considerably faster. Okay, and that makes those algorithms actually hard. Okay, the reason that we do ripple carry is because it's a lot easier. Okay, but the reason that we do much harder algorithms in computers is because they're a lot faster. Okay, and they may also require fewer gates. Okay. So they're just big wins all around. Like for multiplication, there's a really good algorithm, but it's actually based on the fast Fourier transform. So we need to kind of verify that those algorithms work, that our chip works correctly. Okay, and that's really hard. and that's why we have to use proofs. Okay, so so that's I mean that's the reason that we do proofs, and you know what, those proofs are so complicated that is the reason that we want tools that will help us discover those proofs. And you know, like ACL2, or there's a handful of others like Isabel, for example, that you could use for this. Okay. Anyway, that's one thing, right? So we've covered some of the other operations, division, multiplication. Let's talk about a different setting, which is I don't want n-bit numbers because that's too limiting. What if I want bigger numbers? Okay. So let's see what we have. 32 bits. The largest 32-bit number is about 4 billion, okay, with a B, 4 billion. That's a pretty big number. If you actually have a signed, then we have to halve that because, you know, half are going to be positive, half negative. So if I have a signed 32-bit number, then it's as big as 2 billion, okay? Now, how much is 2 billion? I mean, it's such a hard number, right? You know, I mean, I can't wrap my head around it. So here are some kind of yardsticks that we can use. The distance to the moon is about 400 million meters. Okay, that's a lot less than 4 billion, right? Okay, so that's good, right? Actually, it's not that much less. Okay, it's about 5 times less, but still, we could store that. Okay, how about the distance to the sun? Well, now it's 150 billion meters. So we couldn't store that in an integer in a regular computer, certainly not in 32 bits. Okay. How about the distance to the nearest star other than the sun? That's a trick question, right? What's the distance to the nearest star? But other than the sun. So that's about 9,500 trillion with a T, trillion meters. Okay. Yeah, that doesn't fit in 32 bits. Okay. Here's another number that we have is the federal debt. It's roughly 19 trillion. I think actually if I were to round that right now, it would round up to 20 trillion. So yeah, it's not quite astronomical in the sense that there's 9,500 trillion meters to the nearest star other than the sun. But that's a big number. Again, something way too big to store in 32 bits. Okay, so sometimes we actually do want to represent larger numbers. And here's the trick: we don't have to do what the computer gives us. Okay, so the computer gives us a 32-bit adder. We don't have to use that 32-bit adder. We don't have to use the 64-bit adder. Instead, we can do it in software. Okay, so what we'll do is implement our numbers, or represent our numbers, not as a word in the computer, but as a list of words. Okay, the easiest conceptual way to think about it is to think of it as a list of digits. Okay, so if I have a number that has 20 digits, then it would be a list of 20 elements, right? The first one between 0 and 9, the second one between 0 and 9, the third one between 0 and 9, and so on. Okay, and that would be a horrible waste, right? Because I have a list of things, I have all the overhead for a list, and I'm only storing a number between 0 and 9, and I have 32 bits. So instead, what you would really do is you would think of it as a base 2 to the 32, right? And you have this very large digits, okay? But everything that we talked about would work. So we would use the algorithms that we're talking about, except we would implement them in software, okay? That's what Lisp does, okay? So the programming language Lisp is actually one of the earliest programming languages around, the other one being Fortran. And Fortran kind of used whatever the hardware gave, and the idea on Fortran was speed, speed, speed. And Lisp said, no, numbers are numbers, and so we have to do the right thing for numbers, and they actually did lists to represent numbers, okay? I didn't know this before I started preparing for this class, but apparently Python does the same thing. I was very surprised that Python, even 100-bit numbers is able to handle. So it must be doing something special. Okay. A lot of languages, right? In fact, I would say that most, if not all, languages will have some kind of library that lets you do arithmetic on very large integers. So, for example, for C and C++, there's something called GMP, which is the GNU Multiple Precision Library, and that does, it's got a representation for numbers, which is based on list, and it'll do multiplication and addition and subtraction and so on. Boost is a very cool C++ library that has many different things, including a large integer package. Okay, if you're in Java, surprisingly, if you're in C++, because somebody just translated the code, then you can use something called AP Floast. Okay, which again is just a library that handles large numbers. And if you're in Fortran, there's something called MP-fun, multiple precision functions that actually does that, right? So it can handle small numbers, it can handle big numbers. Okay. If you're doing encryption, when you're doing encryption, one of the things that you do is you take a text, and let's say that we take 64K, it's a pretty large chunk, right? 64K of text, and then we're going to encrypt it. They do it as a block at a time, so a block could be 64K, maybe it's smaller, maybe it's only 8K, but still 8K of text, and you interpret that as a single number. That's 8,000 digits, each of which is, you know, I mean, it's a byte, so it's 0 to 255, right? So 8,255 base digits. Those are big numbers. Those are very big numbers. So it's not surprising that most encryption libraries actually have their own large integer support. They could have used some of these libraries, but the development was kind of in parallel. So a lot of them just do their own thing. But they all have large integer arithmetic. Remember the trick. The trick is don't take what the computer gives you. Instead, do it in software, right? But in order to be efficient, use as much of what the computer gives you as possible. Okay, so maybe don't do base 10, actually could do base 32, or at least base 31, so you can detect overflow. That's awesome for the integers. I mean, that's the entire picture of the integers in computers. How about the real numbers? Well, there's a couple of things you can do. So one of the things you can do is approximate the real numbers with rationals. Okay, so if I have a rational number, and remember that there's a rational number that's very, very close to any real number that you pick, right? So for example, let's pick pi, you know, my favorite irrational number. Well, it's actually really close to 22 over 7. And 22 over 7 was used as an approximation to pi for, you know, centuries. So we could just do that, right? Well, we can approximate any real number with a rational number. And what's a rational number? Rational number is just two integers, right? Is one integer divided by another integer. So what we can do is actually use one of these large precision integer libraries and then keep track of pairs of integers and actually implement rational arithmetic with those, so that a plus b, I mean a over b plus c over d is figure out what the common term is, you know, and then cross multiply, for example, to do the sum. Okay, so that's viable. Okay, another approach is to use fixed precision numbers. And what does that mean? What that means is that we're gonna say, oh, our numbers have so many digits. Okay, so for example, our numbers have in this case 7 digits. Okay, so what you see here is 7 digits. Okay, and all our numbers are going to have 7 digits, and ahead of time we decide what exactly is the number of digits after the decimal point. So we have 4 after the decimal point. Okay, so we simply store everything as integers, right? And we know, so you know, just we know that that all of our answers should have a decimal point 4 digits. Okay, so now when we do arithmetic and when I add them, they're already lined up, so I don't have to do anything special. I can just use the hardware or our integer library. When I multiply them, then I'm going to have to divide by, you know, in this case it would be 10,000, right? But divide by whatever the shift is. All right, so we could do that, right? And we can actually use all of our integer stuff to do real numbers. Okay. Now, of course, you're familiar with a different solution. That is to use what are called floating point numbers. Okay, and so we had fixed precision. We have floating point precision. It's the decimal point that floats. Okay, so I could also call this floating precision numbers. Okay, and the idea is just the same as for scientific notation. So if you have any number, and let's just talk about positive numbers. Okay, then I can write it as a times 10 to the b. Okay. Where a is between 0 and 1, okay, and b is just some integer, right? So those are the kind of the components of any number. What we'll have is a sign bit, because I said only the positive numbers, okay, so I have a sign bit. Then I have what's known as the mantissa a, that's the number between 0 and 1, okay, and I have the exponent b, that's what I have to raise 10 to. Basically that tells me where the decimal point is. Look at 124.93, so 0 is the sign bit because it's positive. A would be 0.12493, okay? And then I'm going to need to multiply that by 1,000 to get the answer, so my exponent is 3 because it's that times 10 to the 3, okay? This is the way that we do scientific notation. Okay, so that's what we'll do, except we're on a computer, right? So we have to deal with finite nature of computers. And what that means is that the mantissa and the exponents are both finite precision. So some examples. If you have a single precision number, okay, single precision that is a float in C, okay, you get 8 bits for the exponent, and you get 23 bits for the mantissa. 8 plus 23 is 31. We have a sign bit, okay. For double precision, it's actually 11 bits for the exponent, so we can actually have larger numbers, and 52 for the mantissa. Double precision gives us two things: bigger numbers and better precision, right? So it's a good thing. Okay. Now I do want to just say that we're doing this not base 10, but actually base 2. Okay. It could even be base 16. Okay. Anyway, one of the consequences of this is that the numbers are not evenly spread on the real line. Okay. Now, why is that? Well, let's look, for example, at a times 10 to the 0. Okay, this is just a minus a plus 1 times 10 to the 0 minus a plus 1, right? That is 1. Okay, so those numbers are actually, even though it's quote the next number, right, from a to a plus 1, they don't differ by much. Okay, but now let's look at a times 10 to the 1 minus a plus 1 times 10 to the 1. Okay, so my exponent has gotten bigger, and all of a sudden my numbers, the next number is even farther apart. Okay, because bigger exponent. What that means is worse precision. Okay, so that's something to keep in mind, right? And that's one of the reasons why, for example, when you're doing numerical algorithms, you try to scale things so that you're in the region where the precision is highest. Okay. Anyway, let's look at. I'm sorry. The mantissa actually has the same problem. When you add numbers that are in different ranges, okay, then you're going to lose precision, because I'm going to have to kind of scale the numbers so they have the same exponent, and then I can add them. And when I do that scaling, I can actually, whichever one has the highest exponent won't have as good precision. So something will go wrong, right? So let's see if that's true, right? And we can try this in C, right? So I have two numbers. I have A and B. A is 1,000, B is 0.001, okay? Notice there's like 7 scales, right? Orders of magnitude between those. And let's see what A plus B is. And the answer is 1,000.00977. As you can tell, this is actually awfully close to the correct answer, which is 1,000.001, okay? So it's close, but it's not precise, okay? And the reason it's not precise is because, like I said, those are 7 orders of magnitude apart. When he tries to put them together so that he can do the addition, you just don't have enough bits. Okay, so that's happening. How about this case? I have, oh my God, that is 1,000,000, and then what I have over here is 1,000,000th. So basically, it's about 12 orders of magnitude difference. And if I add those two, I completely lost the B, right? Because when I add such a tiny amount, such a large number, the tiny amount doesn't stay, doesn't stick. Okay, so wow. Okay, and that's with real computers. Okay, okay. So let's kind of tidy all this up, right? What have we seen? We've seen how to build circuits for integer addition. Okay, simple circuits for integer addition. I mean, if you take the circuits course over in the electrical engineering department, then you might actually build some of these. Okay, that's kind of the part and parcel of that. Now we could build more. I should say, by the way, the microprocessors course. Anyway, you could actually do things like faster algorithms, like carry look ahead. Okay, and if you do, you'll get a better results. Maybe with fewer chips, maybe with fewer smaller power requirements. But much more complicated. Okay, same goes for multiplication. Naive implementation, which is the one we talked about, requires n squared full adders, right? It required n minus 1 ripple carry head, ripple carry adders. A better implementation actually only requires n adders, so fewer adders, and it's a lot faster, right? It's actually n log n instead of n squared. And how can you get better speed and smaller circuits? Actually, the reason is that they loop. Okay, so you get the answers and then you feed that back into the thing, and that only works when you have a clocked circuit. But that's the way those are built. They're very, very complicated algorithms. It's actually quite interesting to see how those are done. I have a great deal of respect for the double E's, but don't tell them that. Okay. Anyway, then there's floating point numbers. Okay, and floating point numbers, they have very, very subtle algorithms. Okay, even simple things like addition are tricky because you have to line up the exponents. Multiplication is tricky. It's all hard. And you could actually come up with kind of quote simple algorithms that would be too slow, and it would still be complicated. The real algorithms that they use are extremely complicated. Like for example, for division, to divide x by y, the first thing that they do is they figure out what y inverse is. 1 over y, and the way they do that is they start by doing a lookup into a table. So maybe we don't look at all the bits. We'll look at some of the bits and go, so 1 over y must be really close to a fourth. Okay, and close, not exact, right? So then they'll use an algorithm that will start at a fourth and then kind of slowly, well, quickly work its way to the correct answer. Okay, which might be say 4/15 or something like that, right? So the important thing is that these are complicated algorithms with a lot of really subtle corner cases, and the only way that we can live with that is if we have proofs. Okay, we can't just test, because just consider how many 32-bit numbers I can divide by a 32-bit number, right? So that's like, goodness, did we actually say 4 billion? 4 billion? So that's 4 times 10 to the 9th. If I pair those up, that would be 16 times 10 to the 18th, right? That is a huge number. We're not going to come close to that with testing. So we really need proofs. And the proofs are so hard and so tedious that we can't do them by hand. We need mechanical help. I mean, we need computers to help us do this. That's the state of the art. That's actually the way that hardware companies do things.